Okay. Hi, folks. All right, we're back with question 10 on the practice problems. Based on their Lewis structure, which would be the easiest to break apart? So we have three molecules. We have C2H4, PN, so phosphorus mononitride, and then the hydrogen molecule, hydrogen in its elemental homonuclear diatomic form. So which one is going to be easier to break apart? So what you're looking for in a question like this is which one has double or triple bonds, because double bonds are nearly twice as strong as single bond, triple bonds nearly 3 times as strong as single bonds, but not quite. So we're looking for double and triple bonds in this case. So I kind of drew out a little bit. I hope you can see. So C2H4, you always have 2 carbons bonded to each other, and then divide up the hydrogens, put 2 hydrogens on one carbon, 2 on the other. Symmetry is a big rule when you're dealing with larger and larger molecules of covalent compounds, so you really want symmetry. So each carbon, maybe I'll bring it over here and let you look. Each carbon will have 4 electrons around it, the green ones. Each hydrogen, of course, comes with 1, so you can see how they fit in pretty easily. But then each carbon has 2 unshared electrons left. Let me aim better. So what to do with those guys? Well, they'll form double bonds. So carbon will, where's the green? Carbon will pair up these 2, pair up these 2, and form a double bond between the 2 carbons. So what you'll end up with is a carbon double bonded to another carbon with this pair and this pair. And then they'll have a hydrogen here, a hydrogen here, hydrogen here, hydrogen here. So each carbon feels like it has 8 electrons, 2, 4, 6, 8. And for the other, 2, 4, 6, 8. And each hydrogen feels like it has 2. So they all have their full outer shell. An octet for carbon, and of course hydrogen only 2. So then if you look at PN, you know that phosphorus and nitrogen are both in this row, which has 5 valence electrons, 1, 2, 3, 4, 5. So they each have 5. I drew phosphorus pink and nitrogen green, and so they are like that. The camera. So then you have to figure out what they're going to share. Well, there's only 2 atoms in this molecule, and they have 3 unpaired electrons each, so they're really going to share a lot. They're going to share this, they're going to share here, and they're going to share there, because everybody has to get a friend when you covalently bond, pretty much. So they're going to form a triple bond. So you'll end up with P triple bonded to N, and they'll each have their pair that they already had. So they'll feel like they have 4 pairs around them, 2, 4, 6, 8 for the phosphorus, and 2, 4, 6, 8 for the nitrogen. So we've got a triple bond. Probably that's going to be the hardest one to break apart. We've got a double bond there. That's not quite as hard as a triple bond to break. What do we have with hydrogen? Well, hydrogen, each of the 2 hydrogens has 1 electron, so they're going to share those between them, which is why they form a homonuclear diatomic, giving you hydrogen single bonded to hydrogen. That single bond, of course, will be the easiest bond to break, just because it's a single bond. So number 10, pretty obvious, hydrogen is going to be the easiest molecule to break apart. And then the C2H4 would be next. The phosphorus mononitride would be the hardest to break. And we'll clean the board. Let's see. I had a paper towel. Here it is. Okay, we'll try to dry it off. Windex is made of ammonia, a covalent compound, NH3. which is a great solvent, and if you don't really dry it, it will dissolve what you're trying to write. It's inconvenient when you need to clean your board quickly, but this marker won't come off if I don't do it. So let me make sure we're aimed while that dries. Okay, not too bad. I'll try to get as close as I can so you can see just as well as you can. Okay. So that's all the practice problems. Remember from last week, when you're dealing with naming ionic compounds, so switch gears to ionic here, you just simply switch their charges. So we'll look at a few examples that will be similar to what you'll see on the test. So I want you to look real quick at potassium nitride. Let's see. So potassium nitride is a K and N thing. Iron 3 sulfide, well, when you have a Roman numeral, of course, on the cation, that gives you the charge. So iron sulfide and magnesium oxide. Okay. So make sure that you can write their chemical formula knowing that. Look at the periodic table. Potassium here in the first row is going to form a 1+ ion. Nitrogen here, it's a nonmetal, so it wants to gain electrons. It'll need to gain 1, 2, 3 to fill its octet, so it's going to form a 3- anion. Maybe I'll scoot this down here. So you just switch their charges. So you give the K its friends 3, you give the N its buddies 1, so you get K3N, that's potassium nitride. So for iron 3 sulfide, look at the periodic table. Sulfur needs to gain 2 electrons to fill its octet. It'll form a 2- anion. So then you switch. So iron will get the 2 from sulfur. Sulfur will get the 3 from iron. Always write the metal first, of course. So Fe2, S3. Magnesium oxide, remember to reduce because magnesium forms a 2+ cation, oxygen a 2- anion. Then you just switch, so you don't write Mg2O2, you just write MgO, magnesium oxide. So quick review of last week, how to write the chemical formula for those ionics when they form. Next week we'll talk about polyatomic ions. And just pay attention here. When you're studying this week, you might want to flip ahead and get a jump on studying for a quiz. There's a chart in your book of polyatomic ions in Module 9 that you'll need to memorize. And you'll have a big quiz on that the week you get back from Christmas. So as soon as you come back after the new year, you're taking a quiz first thing. Start memorizing them now. They're a little tricky, but we'll definitely go over it next week when we meet. So, let's see. I think that's all I need to talk about on that page. So, Lewis structure, extra practice. I want you all to, no, I'm going to move on, and then I'll put that up on the next video. So, we're on extra practice problems. If you haven't done them, pause the video and do some. And I'm going to start with problem number 2, aluminum oxide. So, aluminum, if you look, it is going to give up, since it's a metal, 3 electrons, so it'll form Al3+ cation. Oxygen, it's going to give up or gain 2 electrons. Then you just switch, so you get Al, it gets oxygens 2, oxygen gets aluminum's 3, so aluminum oxide is going to be Al2O3. That's kind of weird. There's no B on extra practice problem number 2. There's like A, but no B. Well, the next one's calcium sulfide. So look at your periodic table, calcium sulfide. Calcium's in row 2, so it forms 2 plus cation. Sulfur, here it'll want to gain 2 minus anion. So then when you combine, you reduce, of course, so you just write CaS, calcium sulfide. Easy peasy. Extra practice problem 2, part D, chromium 3 chloride. Well, that tells you right off the bat that you have a 3 plus chromium. Well, that marker doesn't work at all. Here we go. Chromium forms a 3 plus cation because it has the Roman numeral 3, and chloride. So chlorine needs to gain 1 electron to fill its octet, so when you switch them, you get CrCl3, chromium 3 chloride. So again, make sure you pause and do these before you see the answers. But that's extra practice problem number 2. Super fast. Okay. Now, extra practice problem, 3 is ionization potential. So these are confusing, and there's one kind of similar with periodic properties on the test. So order these in terms of increasing ionization potential. Okay, well, ionization potential is the amount of energy needed to remove an electron. So how much energy do you need? And you want increasing. So you want the one that requires not much energy to remove the electron. So would that be a metal or non-metal? Well, to remove an electron from a non-metal is very challenging. They want to gain electrons. So it takes little energy to remove an electron from a metal. So you're going to start with metals. Well, let's see. We've got strontium here. Radium down here, and magnesium. So they're all in column 2, all metals. So which one is going to be easier to remove an electron from? Well, in this case, removing an electron will be easier the further you get from the nucleus, because the nucleus is positively charged and attracts those electrons. And the further you get from the positive nucleus, the easier it will be to steal one away. So I would say it's going to be hard to get a magnesium's electron away compared to a radium, because the magnesium electrons are closer to the positive nucleus. The radium is like, 5 shells out from there. So let's see if I'm right. You never know. So it says increasing ionization potential. Okay, so you want to start out with the one that takes not much energy. So that'll be radium, because those electrons are further from the nucleus. And then, of course, strontium, and then magnesium. Being closest to the nucleus, those will be the hardest to get, requiring the most energy, so the biggest ionization potential. So that can be confusing. You really have to think it through carefully. Number 4, which atom has the greatest desire for extra electrons? So it has germanium, calcium, or bromine. So here we've got calcium's here, germanium's here, bromine's here. And which has the greatest desire for electrons? Well, you know, electronegativity is the desire for electrons, and it increases as you go from here to here, making these guys in row 7 the biggest electron hogs in the world. So bromine will have the greatest desire for an extra electron. It only needs 1 electron to fill its outer shell and have 8, an octet. So it has the biggest desire for electrons. Of course, germanium's a metal, calcium's a metal. They don't even want electrons. They actually want to get rid of electrons to fill their octet, because it's easier to fill it by getting rid of and becoming like argon. So definitely bromine's going to want that electron more than anybody. Number 5, order in terms of increasing atomic radius. So we've got phosphorus, magnesium, aluminum, and argon. Magnesium, phosphorus, aluminum, and argon. So we're going across that row. You're going to order in terms of increasing atomic radius. So this is that kind of counterintuitive one where as the nucleus grows larger, has a larger positive charge, so it will attract even more. So magnesium is going to have the biggest nucleus, the biggest atomic radius, because its electrons will be just a little further. The increasing charge on the nucleus will attract and attract in. So argon will have the smallest nucleus, even though it has the most electrons and the most protons, just because that stuff is pulled in a little closer. So magnesium will have the biggest nucleus, atomic radius, and argon will have the smallest, which is very counterintuitive, but that's the case. Let's see. So, what is the Lewis structure for NF3? Alright, so we have NF3. We're going to think nitrogen has 5 outer shell electrons. Fluorine, each of those will have 7. So, put the one in the middle that has the most empty seats. So, nitrogen has 3 empty seats. Fluorine only has 1, so we put nitrogen in the middle. So 1, 2, 3, 4, 5. This one's super easy because the fluorines, they'll just plug in. And then they get their dots. Like that. Then everybody feels like they have 8, and that's great. And you can, of course, it's impossible to erase on this board, so I'll just do it this way. You can just replace those dots with a bond. So you have single bonds, nitrogen to fluorine in all these cases, plus nitrogen's unshared pair right there. Probably I'm on YouTube time limit, so we'll pause.